Why is fluid turbulence so chaotic, like a butterfly effect? Imagine watching a small ripple in a pond suddenly turn into a wild storm of waves and splashes. That's a perfect way to picture how turbulence behaves in fluids. It's like a tiny spark that can ignite a huge fire. When fluids flow fast or become less viscous, they switch from smooth, orderly movement to chaotic, swirling chaos. This change is called turbulence, and it happens when the flow reaches a high Reynolds number, which measures the balance between inertial forces pushing the fluid around and viscous forces trying to keep it steady. Now, turbulence isn't just random chaos. It's driven by the fundamental equations that describe how fluids move, called the Navier-Stokes equations. These equations are nonlinear, meaning small changes in initial conditions can cause big differences in how the flow develops. Think of it like a tiny gust of wind hitting a cloud of smoke. That small push can turn into a massive swirling vortex. Because of this, predicting exactly how turbulence will behave at any moment becomes extremely difficult. This is where the idea of the butterfly effect comes in. Named after Edward Lorenz, it shows how tiny differences at the start of a process can lead to wildly different outcomes. In fluid flow, a tiny irregularity, maybe a small bump on a pipe wall or a slight variation in flow speed, can grow exponentially. Over time, this small disturbance can turn into large, unpredictable eddies and vortices. It's like trying to forecast the weather months ahead. Tiny shifts in temperature or pressure can change everything. In turbulence, multiple scales of motion interact. Small eddies from and merge into larger ones, creating a complex web of swirling flows. These interactions are nonlinear, meaning they don't follow a simple cause and effect pattern. Instead, they amplify tiny disturbances into full-blown chaos. This process is called energy cascade, where energy moves from large motions to smaller ones, and vice versa, making the flow even more unpredictable. Scientists measure how quickly small differences grow using something called the Lyapunov exponent. The higher this number, the faster tiny changes explode into chaos. In highly turbulent flows, the Lyapunov exponent is large, indicating rapid divergence of flow patterns. That's why even the tiniest change in initial conditions can lead to a completely different flow pattern later on. For engineers, understanding this chaos is vital. Whether designing aircraft, pipelines, or chemical mixers, small uncertainties can impact performance and safety. To manage this, engineers use statistical models and computer simulations that average out the chaos, giving reliable predictions despite the unpredictability of individual flow details. So, turbulence's chaotic nature is rooted in the nonlinear equations that govern fluid motion. Small initial differences grow exponentially, creating complex, unpredictable flow patterns. This sensitivity to initial conditions is what makes turbulence resemble the butterfly effect. Tiny changes can lead to big, unexpected results, making it one of the most fascinating challenges in fluid mechanics.